Sir, excuse me. Hello, sir.
Oh yeah, hello.
Yeah. While we're waiting, can I ask a question, sir?
Oh yes, yes.
It's about Fourier transform actually. So I'm still confused when we are transforming from time domain to frequency domain using Fourier transform. What is the amplitude in the frequency domains means?
Amplitude in frequency domain.
Yeah. For example, we have like a signal from maybe voltage versus time versus voltage, and then we transform it to frequency domain using Fourier transform, and then what the amplitude or the x-axis in the frequency domain
Okay, okay.
represent.
Yeah, yeah. I understand what your question. Yeah, for example, let's say we have xt here. Let's pick up some signal, and then this is the amplitudes, and this is the time domain, right? And let's say the xt become sinusoidal signal, so become like this. So this is the amplitude, maybe become 1 or -1, okay? And then when we transform into the Fourier, using Fourier into a frequency domain, so we can draw being like this. So this is actually the frequency component, and this is the magnitude. The magnitude is similar to the amplitude, actually representing the energy of the signal. Okay, and this please take a look in the x-axis. This is a frequency. Frequency means that where is the energy of the signal in frequency domain. Where is the portion of the highest energy in frequency domain? For example, we have a sinus 2 pi 1 t. This is 1, yeah. This is 1. Means that f being 1 hertz. Okay. And then uh this is should be like this. This is 1. The f itself has a unity hertz. The signal is being like this. And since the frequency has a negative and positive value, so we have become like this. Something like this. Yes. This is the magnitude. And then when we talk, not only the magnitude, we have a second graph as well. This is frequency. This is for phase functions. Yeah, phase functions. And also this phase function is how the phase changing uh, along to the frequency. For example, linear changing means that as the frequency increase, the phase also change linearly, means that the phase is changing, something like this. So if you see in the frequency in the time domain, you see only one graph, but in the frequency domain, you can see into two graph because the frequency has a magnitude and has a phase, something like this. Okay. Is it answering your questions? Or which one still?
Tapi sir kayak magnitude tuh kayak berapa gitu kalau misalkan ditransformasiin kayak gimana ya? Kayak kalau misalkan kita nganalisa suatu grafik, misalkan ya grafik, misalkan A-nya ini tegangan gitu. Nah itu magnitude tuh menggambarkan apa ketika dia ditransformasi ke frekuensi domain?
Iya, tegangan juga. Tegangan juga.
Berarti misalkan contohnya di sini di time domainnya 1 volt gitu.
Ini
Berarti di
juga
sini juga satu gitu, 1 volt satuan.
1 volt, 1 volt.
Oh. Oke, sir.
Oke.
Tapi kok ada yang kayak waktu saya praktikum itu apa telecommunication system,
Ya.
misal kayak dari kan tentang itu ya, tentang amplitude modulation. Nah, itu kenapa dia waktu ditransformasiin ke frekuensi domain, magnitude-nya itu katanya menggambarkan itunya apa namanya? Power apa? Powernya kalau nggak salah apa energinya gitu dalam dB.
Ya, dalam dB sebenarnya kan dB itu the dB itself is comparison between the power signal divided by power noise. dB itself is just a ratio between the power signal and power noise. Usually magnitude ini menggambarkan energi lah, energi. And this energy can has a unit, dapat mempunyai satuan ya, misalkan energi itu kalau dalam listrik itu kan kalau daya itu V kuadrat per R ya. V kuadrat. Nah, V kuadrat ini kan proporsional terhadap tegangannya gitu loh. Terhadap tegangannya. Jadi magnitude ini menggambarkan energi. Energi itu bisa kalau dalam aplikasi nyatanya itu bisa diukur sebagai tegangannya, bisa diukur sebagai dayanya, bisa diukur sebagai energi itu sendiri, satuannya sebagai volt. Karena misalkan kita lihat nih ya, daya adalah energi per waktu, di mana daya sendiri itu adalah I atau V kuadrat per R. Artinya daya atau energi itu proporsional terhadap tegangan sebuah sinyal. Kira-kira seperti itu.
Berarti ini bisa kayak mempresentasikan daya, bisa juga mempresentasikan energinya gitu.
Iya, iya.
Tapi kayak kita bisa langsung ngambil, misalkan kita ditanya energinya gitu ya. Kita bisa langsung ngambil angkanya itu dari grafik frekuensi domain ini nggak? Apa?
Bisa. Jadi energi itu adalah grafik luasan di bawah grafik ini. Energi itu luasan di bawah grafik. Luasan di bawah grafik. Proporsional ya. The energy is proportional to the area of below the graphic ya. In this case, misalkan ini contohnya adalah sinus, berarti energinya itu dia berlokasi di 1 Hz. Energinya itu terkonsentrasi di situ. Apabila ini frekuensinya di sini adalah 1 Hz. Nah, kalau dalam domain waktu energinya kan di bawah sini ya. Itu energinya di bawah sini. Dikuadratkan kan. Kalau tegang energi kan berarti V-nya dikuadratkan. Integral kuadrat gitu kan. Integral tapi fungsinya dikuadratkan. Nah, kalau dalam domain frekuensi energinya ya di bawah sini. Kalau kita lihat kita lebih mudah melihat komponen energi kita lebih mudah melihat di frekuensi mana energi itu ngumpul. Nah, in which frequency the energy is concentrated. Yeah, concentrated in, for example, in this case is 1 Hertz. So the signal in frequency domain will become like this. Means that the energy is concentrated in the frequency 1 Hertz. Something like this. Ada pertanyaan? Silakan. Any other?
Berarti energinya tuh area under the graph-nya ini ya?
Iya, iya.
Tapi kalau puncaknya itu kayak ya amplitude tadi balik lagi itu berarti merepresentasikan tegangan ya?
Merepresentasikan tegangan.
Berarti 1 volt juga ya?
Iya, 1
Satu
volt
juga
juga.
ini puncaknya
Iya,
ini di sini.
iya, iya. Kalau memang benar-benar ideal ya, teorinya begitu. Jadi apa namanya, daerah dalam satu grafik dalam 1 detik gitu, ini juga 1. Karena idealnya lurus aja gitu loh. Idealnya lurus aja. 1.
Kalau seandainya 2 berarti 2 gitu ya?
2.
Berarti itu kayak merepresentasikan ketika di frekuensi sekian itu amplitude sinyal di time domain-nya tuh sekian gitu. Kalau kita
Yes.
transformasi.
Iya, iya. Sebenarnya itu aja. Kita melihatnya begitu.
Oh.
Another,
Clear.
yeah. Maybe another example. Allow me to show you some another example. So, for example, if we have another signal, let's say this is xt and this is st. Let's say st. St still a sinusoid signal, but the frequency is higher. I mean, double than xt. Something like that, but with same amplitude, let's say 1. And then, so the ST is still sinusoid 2p, and the frequency is 2, right? The frequency is 2. Means that in one period, how many wave frequency means the meaning of frequency. So here, so if we transform the ST signal into frequency domain, this signal will be like this. Yeah. So there is exists a signal in 2 Hertz with same magnitude. Yeah, with same magnitude. Something like this. Okay. Okay, is that clear?
So sir, if the signal is combination between these two signal, then when we transform the signal in time domain to frequency domain, then we will have two spikes like in 1 hertz and 2 hertz.
Yes, correctly. So it is fulfill the characteristic of superposition. So let's say I make a new page here. For example, yeah, we have let's say GT consists of XT plus ST, let's say, and the XT is a sinus 2 pi 1 T, yeah, plus sinus 2 P 2T, means that we focus here, the F is 1 Hertz, and this is the F is 2 Hertz. So when we transform to the Fourier, to the frequency domain, let's say j omega equal to x j omega plus s j omega. So this is will exist like this. Yeah, it's just superposition. So this is the frequency domain and this is the magnitude. Just superposition, something like this. So so everybody, I hope it's clear. I want to let you know some example. For example, you have a radio FM, yeah, radio FM device. Maybe your phone, maybe this is an old technology, but radio FM, actually the antenna itself receive signal from many station, right? Many broadcasting stations. Let's say Prambos. Let's say El Sinta. If you know, El Sinta works in 90 megahertz frequency. Prambos, I a bit forget, but let assume
102.2, sir.
102.2.
2.2.
Okay, okay, thank you, Hanif. And then actually our radio receive signal simultaneously from two station, right? Yeah, receive two signal something like this, and then for example in this point lah, if you probe using spectrum analyzer, this is a spectrum analyzer, and the spectrum analyzer will show this is the magnitude, and will show that, let's say this is a 90 megahertz for El Sinta, and this is a Prambos 2.2, and the signal will be like this. Something like that, okay? Yeah, there is access to signal, means that coming from two different station. This is from El Sinta and this is from Prambos. Yes, something like this. In this point. But, not but. And then in this case, you control by choosing only one station, because the speaker cannot make a voice from two station, right? So you have to choose one of them. Let's say you choose Prambos, and then technically, this signal will be filter, yeah, will be filter. So the filter is should be like this. The green color is a filter characteristic. This is a filter. So we have the output. The output here is only the signal. In this point is 102.2. You want to hear only the Prambos. So this is the signal that come out to the speaker, and then you can enjoy the station of Prambos. Okay, is that can you can imagine how the system works?
Yes, sir.
Okay, okay, okay. What maybe once more, if you consider this is an input signal, and actually the filter, this is the the system signal, system function. If the input is xt, and then the system they represent ht, something like this. Okay, this is how your radio station device works in perspective of signal and system. And most of system, particularly in general, we can make a similar understanding, using this procedure. Okay. 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 Is there any question? No. No.
For me, no, sir.
Okay. 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 Let's continue. Assume that this is xt. The xt is the signal we want to transform. Yeah, this is the signal in time domain that will be transformed into frequency domain x j omega. And this xt can be classified, if you remember, from the elementary signal, can be distinguished based on the periodic and non-periodic. And then we can write like this. And also we can distinguish between the continuity and non-continue. For example, periodic and non-continue is like sinus to be t. This is a periodic and non-continue because yeah, something like this is periodic. Periodic but non-continue or discrete Yeah, still we can use a sinus, but in discrete representation. For example, the signal like this, like this. Yeah, this is a periodic but non-continue. Okay, and then for non-periodic and continue, non-periodic continue, for example, E exponential power by t, so we can write thing like this. Yeah, and for non-continue, yeah, we can just power by n. So we write thing like this. Yeah. Okay. And so on. This is t. Okay. And this type of signal has a different method. Yeah. For periodic and continue, we can use a Fourier series. Periodic non-continue Fourier transform. Periodic non-periodic continue. Oh, sorry. This is discrete time Fourier series. Yeah, because periodic, we consistent to use a series. For non-periodic continue, this is Fourier transform. Non-periodic and discrete time Fourier transform. Okay. I hope until this point it is clear. And then how to transform using this method each respectively, and then we can move forward after this. Is there any question? No? No, I will open the another. Okay. Can you see my screen? This is consists of PowerPoint, PDF PowerPoint.
Not yet, sir.
Not yet. Okay, wait a moment. I just drop screen and then I will show this one. Okay. Yeah, right now, can you see my screen? Yeah.
Yes, sir.
Okay. I will directly go to the example 3.1. 3.1. Example 3.1. This is in your PowerPoint that I already share in a mass. Impulse response of the system relating to the input voltage to the voltage across the capacitor in figure 3.2 is derived in example 1.29 as like this. So this is the system function in time domain, because you can see here in t, and the system function has a mathematical expression like this: 1 by RC exponential power by minus T by RC UT. And the problem is find an expression for frequency response and the plot magnitude and the phase response. Okay. Okay. Move forward to the next. Okay. You can see here. This is the Actually, this is a circuit, electronic circuit. The electronic circuit has the input here, input voltage, and then has the R, the resistor, and has a capacitor. And this system actually has an output as a voltage at the capacitor, voltage at the capacitor. So this system has been identified as HT, right? HT equal to 1 by RC I minus T RC UT. If we draw in time domain, is like this, yeah. The graph is being like this, and then this function will be transformed in Hg omega, or in frequency domain. Okay. First, we have to identify this function. Sorry, this function. Yeah, this function. In your opinion, what kind of signal? Sinyalnya jenisnya apa? Kalau berdasarkan dibagi menjadi continue dan non continue, kemudian discrete, periodic and non periodic. If you see the graph, this is continue, yeah, continue and non periodic. Continue and non periodic. So this is continue plus non periodic, because this is continue and non periodic, we use what? Fourier transform. Fourier transform. Yes, Fourier transform. And Fourier transform. Maybe you can open again your notes or your lecturer notes from engineering mathematics, how to transform using Fourier transform. Yeah, if you want to explore more. But in this case, I just let you know that the Fourier transform, let's say, for example, x j omega, this is the signal in frequency domain. This is integral from minus to the positive. This is xt, signal in time domain, times a j omega t dt. Yeah, something like this. J, you can, this is the basic formula, yeah. But you can open, yeah. This signal system, no need to remember, but at least you have to know how to use it. This formula, you no need to remember, but you have to know when and how to use this formula. So in this case, you remember here, I will make a focus here. This is the basic formula, and for this component, this is the HT, right? The HT. So we simplify, we conduct the integrations Yeah, this is a calculus integrations. You make an integration, and then, for example, from this one to this one become this form. If you notify that the limits changing from minus infinity to the zero, why? Because of this function, unit impulse. Do you remember that the unit impulse only exists when t greater than zero? That's why when t less than zero, the signal is zero. So we can ignore. So the integration is only exists from zero to the positive infinity. And then after that, you can derive using a calculus, and then we can get the final expression of hj omega. And then this is a function in frequency domain. Then we have to express this function in magnitude and phase response. Magnitude and phase response. For example, here, because this is a complex number or complex function, we decompose into magnitude. Actually, this is the real component. The phase response is no, not real component. The magnitude is representing the power or energy of the signal. And for the phase, we can see the characteristic of how the signal changing, yeah, how the phase changing respect to the frequency. So the phase, you can see this is the R inverse tangent of omega RC, something like this. So if you see this function, the two function here is a function of frequency, function of omega, because omega itself is 2 pi f. This function of frequency. Okay. Any questions? How to derive? So in this slide, we want to I want to point out first how to choose uh, the right method. The right method, and then uh, how to express magnitude function and the phase function as a function of omega. Okay. If you already know how to choose, and then enough. And then how to express the magnitude response and the phase response, and then enough. Okay. Is there any question?
Sir,
Yes.
I don't know if you have explained it or not, but what is the formula to find the magnitude and phase response from this Fourier transform?
Oh, okay. You can see here, this is the complex number, or complex function lah ya. Why we can see here this is complex, because this is consists of a complex symbol, and you can see here actually we can write as if you see here is RC, rewrite, yeah, I will rewrite, and then this is J omega. And we can conduct in bahasa is rasionalisasi. I don't know in English, is that correct if we say rationalizations? So we just make RC minus J omega super RC minus J omega. And you ever heard about the rationalization? No?
Yes, sir. I've heard.
Okay, RC and then RC minus J omega. So this is become RC this is minus J omega square, right? J omega square, so become RC. This is super RC minus J omega and become super RC minus, this is minus, we can plus like this, right? So is that correct? Because G power by 2 or G square become -1. -1 times minus become positive, something like this. And then this one and become super RC times super RC plus V, and this is super RC minus J omega. This is a real number, right? Real or constant. No. I mean, no. Yeah. This is a real component. So in this case, this is the complex component. This is a complex component. Because this is a complex component, we you remember A plus IB, the magnitude become something like this, I plus B, something like this. So if this is A and this is B, and then you can substitute, become this and this. Once you get this one, and then let's say this is A, and then just multiply by the magnitude of this component. Let's say this is Y, and this is magnitude of Y. This is multiplication. And we got this, the final of result. The final result, something like this. Should we continue, or we just enough?
So it's just like finding the magnitude of a complex number.
Yes, magnitude of the complex number.
So for the first, it's also like finding the argument of a complex number. by
Yes.
finding the angle.
Angle.
Oh,
Yes. Yes.
oh, okay, sir. And also, sir, what
Mm.
does the magnitude represent again?
Here.
Yeah, yeah. What does this? Yeah,
It's
what
depend.
does
Yeah.
that
It's deep.
represent?
Okay. I wait a moment. It's depend on the unity in here. Wait a moment. Depend on the unity of H. Yeah. The unit of HT. For example, if the unit is voltage and then the magnitude we can draw as a voltage. This is as a voltage.
Voltage within frequency domain.
Yes.
Oh, okay, sir.
Okay. Is there any question? So we move forward to the next. You can see here. This is the magnitude component, and this is the phase component. And you can see here the profile of a signal in frequency domain. And the x-axis here is the omega, because you remember the magnitude itself is a function of omega, right? Akar omega kuadrat plus super R C kuadrat. This is a variable. The omega is a variable, so it's changing something like this. And you can see here the highest peak magnitude is 1. It is proportional to A minus T, yeah? Super RC. This is 1 also. And the location of RC is here. Super RC. Maybe some of you asking why the negative component exists. Yeah, this is a properties of a signal in frequency domain. There is exists in positive and negative component. And then also similar to the phase graph, you can see here. You remember, wait a moment. Yeah, this is minus R inverse tangent of omega RC. So still the omega is the variable. So it's changed respect to the omega, and you can see here the graph is like this. Okay. Okay. That's enough about how to represent. So in this slide, I want to point out that we are plotting the magnitudes graph and the phase graph. If you already understand about how to plot the magnitude and phase graph, and that's enough. And talking signal in the frequency domain, mostly focus on this, how to represent the signal in the magnitude expressions and in phase expression. Okay, is there any question?
I think no, sir.
No, okay. So until this point, we already discussed how to transform, not how to transfer, yeah. Actually, how to use the Fourier transform. How to use Fourier transform in frequency in transforming the signal, the signal, yeah. And then we can move, yeah. Yeah, this is a summary, and then we want to show you some another example. This is discrete time Fourier series. Yeah, we a bit a jump. We already talked about Fourier transform and how to, if we have a discrete signal. Continuous, periodic. This one. Yeah. We want to focus in discrete time Fourier transform, means that the input should be discrete plus continue. Sorry, discrete plus non-periodic. Discrete plus non-continue. Actually, this is totally wrong. Non-continue. Non-continue. Non-periodic. Period. Wait a moment. I make a discrete and non-periodic. Periodic. What is the example? Yeah, for example, you have a rectangular pulse, for example, like this. Yeah, something like this. Yeah. This is the amplitude, let's say X. Yeah, X, but this is a continuous, still continuous. So we have to make it a discrete. Yeah, let's say like this. Please focus on the red one. Red one. And then how many signal you can represent is, let's say, just M, maybe M, yeah, maybe M. Let's say M. So the total from, yeah, total is M. This is M, the total. So we can write this signal Xn as being like this. there is a magnitude is 1 for n less than m. We can write like this: as long as the n less than m, the magnitude is 1. The total is m. Yeah. Sorry, I think I make a mistake. No. Okay. This is double M. Sorry, double M. Double M. So yeah, the total is double M. Double M. Why double M? Because n, this is absolute. Absolute means that if we draw correctly, the y-axis is located here. The y-axis, this is a 0. Yeah, this is minus n. This is n positive. So the total, if only half, this is m. So the total is double m. Okay. Until this point, everybody clear? No? Clear? No? We can continue?
Clear, sir.
Okay. And then we want to transform it, yeah. So in this case, this is xn in time domain. We want to express xn in a frequency domain. Frequency domain. Actually, the x j omega usually become like this. This is the n from 0 to double m. This is x. Yeah. Yeah. Actually, wait a moment. My point is how to express being like this. First, we use a basic formula of DTFT. If you open the DTFT, if we the xj omega equal to, this is minus infinity to the positive infinity of xt times a minus j omega or j omega, ya, n, ya. J omega n. So in this case, the xt, the xn, yeah, I mean the xn, because this is a discrete, sorry. This is a discrete. So in this case, the xj omega equal to minus infinity to the positive infinity, and the xn is only 1 a minus j omega n. But we have to change the limit. The upper limit is should be m, and the lower limit from the minus m. That become like this, yeah. So the final expression is like this. And start from minus m until m. This is actually the function of xn because it's only 1, 1, 1, 1, 1, 1. And then this is coming from the formulation. And then we draw being like this. Okay. And then uh, I write in the previous slide j omega in this case is from minus m into positive m. A, we can ignore the 1 minus j omega n, right? J omega n. And then we can transform like this by changing the start. So let's say the start is 0, and then the upper limit become 2 times m's, and the e powered by j omega m minus m. We change the variable n, become variable m. Actually, the purpose is only for simplifications. And then since the m is just a constant, we don't change the m. The only change is m, so we can write being like this. And then this actually this is if you remember, this expression is geometry series geometry series of, if you remember, something like this. Let's say this is 0 a minus t t. This is the geometry series will be my a1 a minus m plus 1 t, and then divided by a minus the m the m, oh, no, the t is this is become 1. Yeah, something like this. Okay, this is the geometry series in compact version. And then if you are interested in and you can take a look here, there is the value become like this for omega not equal to 0 or 2 pi. 4 pi is like periodic, and then the value become 2m plus n at the omega 0, 2 pi, and 4 pi. And then if you are interested in the mathematic expression, this complex expression will be simplified by sinus, yeah, sinus something like this, divided by sinus something like this. Just I want to point out that if you are interested in the analytical mathematic analytic, you can see and how to derive. But in the signal system, we don't put many effort in this how to derive, because this derivation you can easily find in the table of calculus. But the important thing is how to express this signal in the magnitude and in the phase. It is in the next, yeah. No, in the previous, yeah, you can see here. The upper figure, this is the signal in time domain, yeah. And the lower figure, this is the signal in the frequency domain, yeah, in the frequency domain. And then this is the signal in the phase component. The upper signal is the signal in the phase component, and the lower signal, the signal in the phase component. This is a magnitude component. This is the phase component. You can see here that the magnitude, you can see here, this is the magnitude for the y-axis, and the x-axis, this is the frequency component. In this case, the omega, we use this symbol instead of omega. Maybe some of you asking why we don't use just the similar symbol. Yeah, actually, it doesn't matter. It's just to distinguish between a continuous signal and a discrete signal. And you can see here also the figure also similar. I mean, the x-axis representing the frequency domain and the y-axis representing the phase. And the upper, A and B, sorry, A and C representing how the magnitude change. You can see the peak here is about 2, but in the C figure is around 10. Okay. So move forward to the next slide. You can see here that this is a relationship between signal in time domain and in the frequency domain. In the previous example, we have like this. This is a signal in time domain. And then we got the signal in frequency domain become signum. something like this. And if we have a rectangular pulse in frequency domain, and then in time domain, we have a signal also. Is this phenomena we can see as a, how to say, in first form lah, ya, in first form. From this slide here, this example, we can see ya, bahwa sinyal kotak dalam domain waktu ini menjadi signal signum dalam domain frekuensi, dan sebaliknya sinyal kotak dalam domain frekuensi akan menjadi sinyal signum dalam domain waktu. Kira-kira seperti itu. Oke. So until this point we already talk about the how to use discrete time Fourier transform. Is there any question? So we almost finished for this week, the material for this week. So we cut the material for the frequency domain until this point. So I will summarize. Wait a moment. Sorry for thank you for waiting. Sorry for disrupt you. So in terms of LTE system in frequency domain, we already discussed about how to use or how to use a frequency domain in the LTE system. And then we already conduct how to use this Fourier transform and how to use discrete time Fourier transform. For the midterm exercise, we finish until this point. This is the material for the midterm. And then after midterm, we still continue discussing about the Fourier series and discrete time Fourier series plus time bandwidth product. So this is for after midterm. And then if we wraps up all of the material, so the midterm examinations will cover the introductions of signal and system, and then LTE system in time domain, particularly we are talking about convolution, how to convolve the signal for continuum and discrete, and also how to represent the system in a block diagram, diagram representations, and in the state space. Okay. So also we already discussed, so it will be covered in UTS in midterm as well. System in frequency domain. So it cover for Fourier transform and for discrete time Fourier transform, particularly and how to express the magnitude and phase, as well as this is the magnitude and the phase. And each of them, how to plot the each function here. Is there any question for the midterm examination? And the question will be essay, but what is the number and how long will be informed later. Okay, that's all. Is there any question? If no, we finish our class today and we meet at the mid examination, midterm.
Sir, I have questions, sir.
Yes, please.
For each recording of the meeting, will you post it in a mass?
Oh yes. So I think all of the meeting already posted. Is there any recorded net? Is there any video that not posted?
Maybe I'll check later, sir, because I
Okay.
haven't seen us.
Mm.
But for today's meeting, we also posted in mass, right?
Yeah. Of course.
Okay, sir.
Okay. Is there any other question? So mm, Okay. If there is no question, and then we finish our class today. Thank you very much for your attentions, and see you next week. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Waalaikumsalam warahmatullahi wabarakatuh.
Thank you, sir.
Thank you,
Thank you,
sir.
sir.
Thank you, sir.